Hello, we will talk about the generating functions of sectoral structures today, and we will start looking at some of the algebraic geometry of these graphs as well. So the concept is very simple. If we have a sectoral structure, let's say AN is equal to 3, 1, 2, subscript 6, then the generating function of an, we will write it as an of x, will simply be, we find the order of the sectoral structure, so it's 3, there's 3 parts to it. So therefore, the polynomial will have 3 parts, and the highest degree will be 1 less than the number of parts, or 1 less than the order. So in this case, the order is 3, the highest degree will be 2. So we'll say x squared, and then x, and then a constant, and the coefficients will be the parts of the sectoral structure. So this will give us 3x squared plus x plus 2. And this will really help us as we do some of the algebra on sectoral structures. Let's look at another example. Bm is equal to 4, 1 cubed, 2 squared, 1 subscript 12. The generating function will be Bm of x. And again, we put all the coefficients. And here the order is 1, 2, 3, 4, 5. Sorry, so let me count them actually. So we have 3 and 2 is 5, 6, 7. So the order is 7. So therefore the highest degree will be 6. So we'll say Bm of x is equal to 4x to the 6th plus x to the 5 plus x to the 4 plus x cubed plus 2x squared plus 2x plus 1. So these correspond to these coefficients. Now for these two polynomials that we looked at, we can do a graph for both of them, see what they look like. We can look at their intersection points, and we can see which intersection points maybe correspond to natural numbers. Keep in mind that this operation, if you do it for a sectoral structure or for its reverse, you will get different results. So this is a bound operation where the order is important. In other words, when we're talking about sectoral structures here, we want them in their standard form. So in this next example, we're going to get all the ST3, so all the sectoral structures of degree 3, and we will generate their, we will find their generating functions, and this will give us 3 generating functions. F of x equals 3, f of x equals 2x plus 1, and f of x equals x squared plus x plus 1, and we can study their graphs and particularly see their intersection points as well, and some of the relationships that result from these intersection points. Let's go a little bit higher. Let's look at ST4 group. So the sectoral structures of degree 4, and we have 6 of those, and we can see all their generating functions. This will be, let's say, y equals 4, y equals 3x plus 1, y equals 2x plus 2, 2x squared plus x plus 1, x squared plus 2x plus 1, and x cubed plus x squared plus x plus 1. Now, one important property of all these polynomials is that the sum of their coefficients for all of these is equal to 4. In other words, the sum of their coefficients is equal to the degree of the polynomial, of the sectoral structure. And additionally, the number of parts, or the number of terms in each polynomial, is equal to the number of parts of its corresponding sectoral structure. So here we get this really nice group of polynomials. Again, we see a very interesting intersection pattern. We see, of course, that all the polynomials intersect at 0.15. And then we have two intersection points on the line x equals 0. 3 at the line x is equal to -1. And 3 at x is equal to -2. So, it's very interesting where their intersections of these graphs occur. A lot of them occur at natural numbers. Let's look at something more complicated. Let's look at the ST5 group. And here, these will be, so each of these polynomials, or each of these graphs, is a polynomial corresponding to a sectoral structure of degree 5. Again, a very unique intersection pattern emerges. For example, here we have so many intersection points. And I think actually I made a mistake. I think these intersection points that I read were for this graph, so excuse me for that. Indeed, here we see 0, there's two intersection points. We see at x equals -1, there's a lot of intersection points here. And at x equals -2, we also have several intersection points. And keep in mind, when I say intersection points, I mean the graphs intersecting with each other, not with this line. So this leads us to study another property, maybe it will be simpler that way, which is, let's look at these groups of polynomials, or these generating functions, and study them at a particular value of x. So we will look at the value of x equal to -1. So for example, if I have a generating function that is 3x squared plus 2x plus 1, I will substitute -1 for x and study the resulting pattern, or the result of that. So if we have two sectoral structures whose generating functions are a(n) of x and b(n) of x, and if we use the value -1 for x, and we get a(n) of -1 is equal to bn of -1, we will refer to these two sectoral structures as coherent with respect to each other. And we can study this particular pattern. For example, 4(2) subscript 6 and 141 subscript 6, when we look at their generating functions and we substitute -1 instead of x, we get equal values. So let's double check. So -1. So for 4(2), the subscript 6, the generating function is 4x plus 2. We will substitute -1 for x. We will get -4 plus 2 is -2. Now for 1, we get the polynomial x squared plus 4x plus 1. Substitute -1, we get 1 minus 4 plus 1, which equals -2. So therefore we say that these two sectoral structures are coherent with respect to each other. And it's helpful to look at -1 because it doesn't really alter the coefficients magnitude. It only affects the sign, and in that way it really helps us study the nature of the polynomial. So if we look at ST6, for example, there's a lot of, so I think that includes 20 different sectoral structures of degree 6. And if we calculate the -1 value for all of them, we don't get 20 different values. They're actually nicely divided into 6 groups. Some of them are small, some of them are large, which is quite nice. So some of them are only a single sectoral structure. That's not many, just these two each give us a unique value. But then we see many of these sectoral structures cluster around a single value. So we have, for example, -2. We see that many sectoral structures are clustered around -2. We have some around 4, not many. But then we have a lot clustered around 2. So -2 and 2 have a lot of sectoral structures clustered around them. But then what we really want is the ones that give us a result of 0. And that's also a pretty large group. But that's very interesting for us to study. So this includes, as we can see, all these sectoral structures shown. And so we will call these, the ones that give us a result of 0, as the primary coherent set of a given sectoral structure or subset. So for ST6, these ones are the primary coherent set or subset. We notice that if the degree of the sectoral structure is odd, then we cannot get a result of 0. So there will be no primary coherent set. But if it is even, then we can get a primary coherent set. So here we have ST5, for example. We see that there's three that give us a value of -1. There's 2 that give us a value of 3, 2 that give us a value of 1. So a very interesting pattern, but no, we cannot get a value of 0. Now, if we look at this more broadly, again, we see that for all the odd degrees, we have a primary coherent set that is empty, so 0, size 0. But if we study the sizes of the primary coherent sets of even degrees, we get a very interesting pattern. So 1, 3, 7, 17, 41, and so on. And we see that this actually corresponds to some known patterns that are that could be the Motzkin path related to secondary RNA structure. So as we go through the book, we keep seeing these familiar patterns. So here, this is one more example. If we look at the ST6 polynomials, again, we see a very unique intersection pattern clustering around certain points. Let's look at one more thing related to these generating functions, the graphs of these generating functions. So here we're looking at all the xi structures of different degrees. So remember, those are the structures of the form 1 to the n subscript n. So if we graph all the possible xi structures, or the generating functions of those, of course we see two interesting things. First, we see that they all the graphs intersect at 0, 1. And of course this is easy to prove algebraically, but we just want to observe now the algebraic geometry of it. So they all intersect at 0, 1. However, we see these two intersection points, and those are split based on odd and even degrees. So the structures with even degrees all intersect at -1, 0, and all the structures of odd degrees intersect at -1, -1. And again, we can easily prove this, but the idea here is just to look at the graph. Let's look at all the isomorphic sectoral structures of degree 2. So again, there's many of these, but if we look at a set of degree 2 sectoral structures that are isomorphic to each other, we see that they all intersect at a single point. And again, the algebra of it is easy, but the geometry of these graphs is what we are trying to see. Similarly, if we get isomorphic structures of degree 3 and we graph all of them, we get this concentric set of parabolas like that. Now, what's interesting about these graphs is that we have this very interesting pattern. So when we look at these parabolas or sectoral structures of degree 3, we see that all their vertices lie on the same vertical line. They are all symmetric around that same vertical axis. But very importantly, all these have the same complex roots. So this is, I guess, a more important finding, which we can't easily tell by looking here. But if we get a set of isomorphic sectoral structures of degree 3 and we get their generating functions which form parabolas, all of these parabolas have the same complex roots. Similarly, if we look at degree 4 sectoral structures and we graph all of them, we get this set of degree 4 or degree 3 graphs. And what is very interesting about them is that they all share the same complex roots. And again, this can be shown algebraically as well. So this leads us to a very important rule or concept here. So let's look at this. So if AN and BM are isomorphic sectoral structures, then AN of x and BM of x have the same complex roots. And again, we can show this algebraically as well. We will look at another concept which is a little bit of a generalization of this idea. Now we want to look at all sectoral structures of any degree that share the same parabola on their graph. So for example, now we're looking at the parabolas. So this will include all the or a set of degree 3 sectoral structures. So we are looking at sets of degree 3 sectoral structures that share the same vertex on their parabola graph. We will notice that they all fit, of course, into each other like that. We will refer to these as nested sectoral structures or graphs of nested sectoral structures. For example, the graph above includes 3, 6, 2, 11 and 5, 10, 4, 19. Notice that not just their sectoral or their parabolas have some similarities, but also their sectoral structures have some similarities. Additionally, for these third order sectoral structures, they must have 2 real zeros. So for this to work, for the sectoral structures to be nested, they must have 2 real zeros. But what's interesting about that is that as the degree of the sectoral structures increases, so as the degree starts approaching infinity, we start approaching a sectoral structure that is isomorphic to 1, 2, 1 subscript 4 in this case, so in this particular case. So we start approaching a very simple sectoral structure, so 1, 2, 1 subscript 4. So here you can see as we go towards greater values, the parabola starts closing in on itself as well. But what is 1 to 1? It's actually simply going to be again here it will be a semicircle and 2 quarter circles attached to it. So that's the sectoral structure we're approaching. Here we're looking at another set of nested parabolas or nested sectoral structures. So this is a different set. So here we're starting with 4 squared 3, and we keep going up in our degree. So here really all we do is we keep generating these third order sectoral structures, and if the vertex fits, we include it. If not, we don't. What's interesting is as we go towards infinity, again we start approaching a very simple sectoral structure, which is 2 squared 1 subscript 5. So or we approach something that is isomorphic to it. So what we are seeing in both these examples is we start with these seemingly arbitrary sectoral structures, and we keep going larger in number. However, they do share the same vertex on their generating function, and we end up with a structure that is isomorphic to something very simple. So 1, 2, 1, 4, and in this case 2, 2, 1, 5. So we will stop here. Now in the coming lessons we will see why we generated these, why we looked at generating functions, because this will help us a lot to study the algebra of the sectoral structures.